All right, today we are going to be starting Unit 5. I apologize that I'm not there today, but what we're going to do is follow through in the new note packet, which is starting our Unit 5 Analytic Trigonometry. This particular unit has a very heavy focus on algebra and our understanding of using algebra and trigonometric identities. So hopefully today won't be too bad. There is a homework assignment. It is already up on Moodle. The questions are highlighted. I have also left some copies of the 5.1 printed out for those of you that want those printed out copies, so make sure you grab those from the sub. So let's go ahead and get started. So our unit looks like this in that we have 5 sections and then we'll have our end of the unit test. Today we're going to be using the fundamental identities. Some of these we have seen before, actually most of these we have seen before. But some are kind of ones that we've formalized. We have kind of touched on them a little bit, but now we're going to formalize them a bit. So our objective today is to recognize and write the fundamental trig identities and then use these identities to evaluate functions, simplify expressions, and rewrite trig expressions. So you're going to notice that we're going to use these identities and kind of move sine, cosine, move everything around, solve for our angle, solve for our x, whatever the case may be. So here are the identities that we need to know at this point. Up here on top, we have the reciprocal identities, which we have seen before, right? Those we have definitely seen. We understand that sine and cosine are reciprocals of each other. We also have these quotient identities. These become really important when we want to put everything in terms of sine and cosine. We have these Pythagorean identities. Yep, we've seen these before. Now, some of the ones that are new, but we have talked about, but they are newer, is the relationship of the complements. So complementary angles. Remember, complementary angles are angles that add up to 90 degrees. So what this is saying is that the sine of a complementary angle is equal to that angle itself. Okay, so things like the sine of 40 degrees is equal to the cosine of 50 degrees because sine and cosine have that relationship, and 40 degrees and 50 degrees are complementary angles. So this whole kind of bracket here gives a definition of the relationship of those complementary angles. The very last section there is our even and odd identities. So for those functions that are odd, we understand that if we plug in a negative value, the sign of it ends up being negative. And you can kind of see where those even and odd identities exist. So for instance, our odd functions are these two sections here. Those are odd. And then our even functions are right here in that when I plug in a negative angle, I get out the positive cosine. And we can talk a little bit more about that. A lot of it comes back down to the graph, right? What does the graph of the sine function look like compared to the graph of the cosine function? The sine function has origin symmetry, whereas the cosine function has y-axis symmetry. Sometimes you're going to see these identities written like we'll solve for the sine. So in this case, we took that first Pythagorean identity and we solved for the sine. When we do that, we have to consider things like plus minus. So there's the plus minus and then our square root. So sometimes you'll see them listed that way. Sometimes we will have to use that information. But that is just taking an identity and moving it around, solving for something in particular. My interpretation is that we all know how to do that. Sometimes as you're working through these identity problems, you won't know what the next step is, and that's perfectly okay. The one thing that you want to do as you try out a path, as you try to figure some of these questions out, is you're always applying an identity or something that you can derive from the identity. All right, let's start working through these examples. So in your notes, we have 9 different examples that are in this section, and because this is a recording, I'm going to do all 9 of the examples. If you're kind of getting the hang of it, you don't have to, but let's go through each example one at a time. And remember, because it is a recording, if you want the sub to pause it, or if you're watching this on your own device, you can always pause it as you go along to get these notes down. All right, we know the secant of u is equal to negative 3/2, and the tan of u is greater than 0. We're going to find all the values of all the other trig identities. We definitely can do this by drawing a triangle, but this whole unit is trying to apply those identities. So I am going to use the identities as I go through and solve a lot of these examples. Since we know the secant is negative 3/2, the cosine is therefore negative 2/3. All I had to do there, right, the reciprocal identity says that I just flip those. I take the reciprocal of secant to get the cosine. So now I'm at a case where I know cosine is negative, and based on the information given in the question, tangent is positive. So I think to myself, okay, in which quadrant is tangent positive but cosine negative? We are in quadrant 3. So we know cosine, we know secant, we've got the other 4 that we have to figure out. Let's start with sine. In order to figure out sine, I'm going to use one of the Pythagorean identities that says sine squared plus cosine squared equals 1. I'm going to plug in the value that I have for cosine. So I get sine squared u plus negative 2/3 squared equals 1. I get sine squared u plus 4/9 equals 1. I subtract 4/9. I get sine squared is equal to 5/9. I then take the square root of both sides and I say, okay, the sine of u is the square root of 5 over 3, right? I had to take the square root of the numerator and the square root of the denominator. Now, before I'm done, I ask myself, in quadrant 3, is sine positive or negative? Well, it's negative in quadrant 3, so therefore the sine is also going to be negative. In order to figure out the cosecant, I'm just going to flip these two over. I get negative 3 over radical 5, but then I have a radical in the denominator, so I need to get rid of it. So I multiply by radical 5 over radical 5. I get negative 3 radical 5 over 5. All right, so we've got cosine. We've got secant. We got sine and cosecant. So the last pieces of information that we need are tangent. So our tangent, that's going to be sine divided by cosine. So I have negative radical 5 over 3. That's my sine. And then my cosine is negative 2/3. But remember, I'm going to multiply by the reciprocal when I divide fractions. My 3's cancel out, my negatives cancel out, I get radical 5 over 2. Then for my cotangent, I'm going to take the reciprocal of the tangent value that I have. I get 2 over radical 5, but then I have to get rid of the radical on the denominator, so I get 2 radical 5 over 5. There's my cotangent. There's my tangent. I now have all 6 of the trigonometric functions based on the information provided to me. I took care of the signs. I made sure so tangent and cotangent are positive. The others are all negative. There we go. You definitely could have done this by drawing a triangle, but remember, I'm trying to use those identities as much as possible. All right, example 2. So we're going to simplify sine of x times cosine squared of x minus sine of x. So as we go through these examples, like I said, you may not always know how to start these. I'm going to try to give you some tips and tricks. A good thing to always consider is, all right, I'm trying to simplify something. Is there a GCF? So looking at these two pieces, right, I have a negative sign right here. So what's common to the first part and also common to the second part? Well, it's the sign of x. So what I'm going to do is factor out the sign of x. What I'm left with is cosine squared x minus 1. All right, let's think about, so now we're kind of here, and I'm thinking to myself, all right, I know I have a Pythagorean identity that says sine squared plus cosine squared equals 1. Well, what is cosine squared x minus 1? Let's see if I can solve this particular identity so that it gives out cosine squared x minus 1. Let's move the 1 over. So I have sine squared x plus cosine squared x minus 1 equals 0. Now I want to get rid of that sine squared x, so I'm going to subtract sine squared x from both sides of my equal sign. So I get that cosine squared x minus 1 is equal to negative sine squared x. So this is kind of what I say, if we can derive something from the identities given to us, we can use those as identities as well. I'm going to take the negative sine squared x and plug it in right there. So I get won't do the negative yet. I get sine of x times negative sine squared x. I then multiply those together. I get negative sine cubed x. So who would have thought that the example we started with is equivalent to the negative sine cubed x that we got in the end? And that is what this unit is all about, moving things around algebraically to simplify or solve or get the left side of the equation to equal the right side, and so forth. Now that we've gotten kind of a taste of factoring, let's factor some more. So in example 3, we're going to factor each of these expressions. So given that the direction says to factor, I know that I have an identity that has tan squared and secant squared in there, and maybe that's what I should be working with. But since the problem told me to factor, I'm going to look at this and say, okay, I have secant squared theta minus 1. Well, you know what? That's very similar to x squared minus 1. It's just in this case, the x is secant theta. How would I factor x squared minus 1? Well, that's the difference of perfect squares which factors as x plus 1, x minus 1. And it doesn't matter in which order, right? I could have put the x minus 1 first. So that tells me the secant squared theta minus 1 factors as secant theta plus 1, secant theta minus 1. All right, let's look at 3b. So I have 4 tan squared theta plus tan theta minus 3. So in my head, I kind of think to myself, that's kind of like 4x squared plus x minus 3. How would I factor this? Well, I definitely am thinking to myself, all right, I got to think of the factor pairs of 4 and the factor pairs of negative 3, and how can I kind of guess and check my way into reverse foiling this? This factors out nicely as 4x minus 3, x plus 1. And if you're not sure, right, you can foil back through to double check your work. Yep, 4x squared plus 4x minus 3x, but yep, looks good as I foil it to double check. So that tells me I'm going to factor this tangent. Wherever I see an x, I'm going to plug in the tangent of theta. So this will factor as 4 tan theta minus 3, and then tan theta plus 1. So there are my factors. All right, moving on to example 4. We're going to factor again. Okay, so I want to be able to factor this particular function. The problem that I see is I have both cosecant and cotangent. I can't factor if I have two different variables, right? In this case, maybe cosecant x is our x, cotangent x is our y. I'm not going to be able to factor this without putting them all in the same trig function. So I'm going to use the identity that cosecant squared x is equal to 1 plus cotangent squared x. So if you look at your identities, you'll see that listed there. So I am going to take this value here and plug it in for cosecant squared x. So I get 1 plus cotangent squared x minus cotangent x minus 3. I'm going to combine the like terms that I have. I have cotangent squared x minus cotangent x minus 2. I did the 1 minus the 3. Now, I've got everything in the same trig function. It's in cotangent, and I'm thinking to myself, okay, this is kind of like x squared minus x minus 2. So how does that particular function factor? Well, I get x minus 2, x plus 1. Okay, I am then going to factor that the same way. In this case, the x is actually cotangent x, so it factors as cotangent x minus 2, cotangent x plus 1. And that represents the factoring of that particular function. Notice I had to use the identity first to get everything in the same trig function. Once I did, I was able to factor it quite nicely. All right, example 5. We got the sine of t plus the cosine of t times the cosine of t. We got a lot going on here. Okay, so what could I do here to try to add these things together? Well, the first things first, I see cotangent of t and cosine of t. I don't like how I have so many different trig functions. I've also got sine thrown in there. So here's kind of a recommendation that I have. When in doubt, try to put everything in terms of sine and cosine. Okay, those are the trig functions we are most familiar with. We have memorized a lot of those identities. So that is as a recommendation. Like I said, when you start out these problems, you may not always go down the right path the first time, but as long as you're applying correctly the trigonometric identities, you shouldn't do anything wrong. Maybe your path takes like 5 or 6 extra steps than a different person's path, but you should still end up with the same answer. So my first thought is, okay, I know that cotangent, I hate that we're using t, but cotangent is going to be equal to cosine divided by sine. So let's go ahead and change that. I'm going to keep the sine t as it is, but I'm going to change this to cosine t over sine t times cosine t. When I multiply my fractions, right, I'm going to multiply my numerators and my denominators, so I'm going to go ahead and do that. I get the sine of t plus cosine squared t over the sine of t. So I'm trying to add these two fractions, and in order to add fractions, I need common denominators. So the common denominator that I see here is the sine. This particular fraction here is missing that, so I'm going to multiply my numerator and my denominator by the sine of t. So I wind up with sine squared t over sine plus cosine squared t over sine. I'm going to add my numerators together, keep my denominator, that's how I add fractions, And then I see, can I simplify anything? Well, what is sine squared plus cosine squared? It's just 1. So I get 1 over the sine of t, which using our reciprocal identities, I can just write as the cosecant of t. Final answer. So that whole problem that we started with can be simplified down to the cosecant of t. Next example, example 6. Perform the addition and simplify. Well, we just did a fraction addition problem, and we saw that in order to add fractions, I need a common denominator. So I've got everything in terms of sine and cosine. I could technically change that second fraction to cotangent, but I don't think that would help me out anyway at all. So I'm just going to go right into what the directions say, which to say to perform the addition and simplify. My least common denominator, well, this fraction here says you need a 1 plus cosine theta in your denominator, and this fraction over here says, well, you also need a sine theta. So that is my least common denominator. I've got to have both of those denominators represented, which tells me, okay, I'm going to have to go back to each of my fractions and see what they're missing. This particular fraction is missing the sine, so I'm going to multiply by 1, or in this case, the 1 is sine over sine. Then I'm going to multiply this one by 1 plus cosine over 1 plus cosine. So let's go ahead and figure out what we get. I get the sine squared theta over that whole mess. And my next one, well, let's go ahead and distribute. So I get cosine theta plus cosine squared theta over that whole mess of the denominator. Then when I add my fractions, I'm going to add my numerators and keep my denominators. So I get sine squared theta plus cosine theta plus cosine squared theta, sorry, that's a cosine, all over all right. Can I simplify this at all? Well, looking at my numerator, sine squared plus cosine squared, that's one of our identities, right? Sine squared theta plus cosine squared theta is just equal to 1. So I wind up with 1 plus cosine theta over sine theta 1 plus cosine theta up. My 1 plus cosine thetas, since these two in the denominator are being multiplied, I can cancel those two out. So I wind up with 1 over sine theta, which is the same thing. Didn't we get this on our last problem? Wasn't that the answer to the last question as well? Cosecant theta. So I added all of that up. I simplified. I had to use my understanding of algebra, how I could simplify these things down, and I wind up with cosecant theta. All right, example 7. Rewrite 1 over 1 plus sine x so that it is not in fractional form. All right, there must be some kind of rule where I have something in my denominator that I'm not allowed to have, and I have to figure out a way to get it out of there. Okay, so this one is definitely a little bit trickier. I'm going to kind of pull off to the side for a second and say, okay, let's talk about from our Pythagorean identity, we know that cosine squared x is equal to 1 minus sine squared x. Okay, all I did in that case is I took the sine squared x plus cosine squared x equals 1, and I subtracted sine squared x from both sides. I'm now going to look at the right side of my equal sign and say, okay, can I factor 1 minus sine squared x? I can. It is the difference of perfect squares, just like we saw earlier when we were factoring. It's 1 plus sine x times 1 minus sine x. So that tells me, okay, this is not a fraction, I just simplified this some more, that this is equal to cosine squared x. 1 plus sine x times 1 minus sine x is equal to cosine squared x. Okay, so if I have 1 plus sine x, oh, that's what's in my denominator here, and I multiply it by 1 minus sine x, I'm going to wind up with a cosine squared x in my denominator. So that's what I'm going to do. I'm going to multiply the numerator and denominator by 1 minus sine x. And I know this is a little tricky. This is not one that maybe would have occurred to us automatically. But this is why we're doing these examples in your notes, so that when you get to the homework, you have all of these different things that you can try. All right, so I have 1 over 1 plus the sine of x, and I'm going to multiply by 1 minus sine x over 1 minus sine x. When I do this, I can see that I get 1 minus sine x in my numerator, and in my denominator, I get cosine squared x. Right, we just talked about why that is true. I wind up with a cosine squared x. All right, I'm still trying to get rid of a fraction. I still have a fraction. They want me to change this so it's not in fractional form. The next step that I'm going to apply is I'm going to divide both parts of my numerator by cosine squared x. I get 1 over cosine squared x minus the sine of x over cosine squared x. All right, I know for a fact for this very first one, this is going to be equal to secant squared x. So that means that doesn't have a fraction anymore. Perfect. Let's see about this next one. I've got the sine of x divided by the cosine squared of x. What if I take this, I'm just going to take it aside for a second, and I'm going to say, okay, this is equal to the sine of x over the cosine of x times 1 over the cosine of x. And I know from my trig identities that sine divided by cosine is tangent x, and 1 divided by cosine is secant x. So there you have it. I have gotten rid of the fraction. There is nothing in fractional form now. The fraction is all gone. That was a tricky one. I definitely would agree that that was a tricky one. All right, we have 2 more examples as part of this note sheet. Example 8 says, use the substitution that x is equal to 2 tangent theta, where theta is somewhere between 0 and pi over 2, or 90 degrees, to write the square root of 4 plus x squared as a trigonometric function of theta. Whew, that was a mouthful. All this is saying is we're going to restrict x, we're going to restrict theta. We have two different variables we're working with here. We're going to restrict theta to be somewhere in quadrant 1, which is going to allow me to apply this function in. So wherever I see an x in this expression, I'm going to plug in 2 tangent theta. So I have the square root of 4 plus 2 tan theta squared. I now am going to multiply 2 tan theta times 2 tan theta. That's what the squared means, right? So I get the square root of 4 plus 4 tan squared theta. Now, I'm going to factor out a GCF under my radical there. I see 4 is common to both terms, so I get 1 plus tangent squared theta when I factor out the 4. Ooh, what is 1 plus tangent squared theta equal to? Looking at our first page of identities, right, I have this identity. We haven't used it yet today, that 1 plus tangent squared theta is equal to secant squared theta. Right? That's an identity that we're going to use here. So wherever I see the 1 plus tangent squared, oops, I forgot my theta, I'm going to plug in secant squared. So I get 4 times secant squared theta. Now, if it kind of helps to remind you that this is equal to the square root of 4 times the square root of secant squared theta, I then take the square root of each part. The square root of 4 is 2. The square root of secant squared is just secant. And there is my answer for that question. All right, for our last example, last but not least, oh my God, there's a natural logarithm in there. Whew. Rewrite the natural log of the absolute value of cosecant theta plus natural log of the absolute value of tangent theta as a single logarithm and simplify the result. Okay, we've got to go back to our properties of logarithms. One of them is the product property of logarithms that we talked about when we expand and when we condense. So when we condense, because remember, we're trying to condense this down. So it says write it as a single logarithm. We're trying to condense it down to 1. Addition turns into multiplication. And hopefully we can remember some of the other ones. Subtraction turns into division. If we need a refresher on logarithms, definitely just kind of Google the properties of logarithms. I'm sure there's a little tip sheet. Actually, I'll put one on Moodle as well, just a little image that shows the different properties of logarithms. I know it's probably been a while since we talked about them. But for this particular example, we have a plus sign. So that tells me I'm going to condense this down to 1 logarithm. So I'm just going to write natural log 1 time. I then am going to change this from addition to multiplication. So I now have this condensed down into 1 logarithm. I only have natural log written once. I'm pretty much there. The second part says to simplify the result. All right, in order to simplify this, I think I'm going to turn everything into terms of sine and cosine and see if I can simplify from there. So I get the natural log of 1 over sine theta times, remember tangent is sine divided by cosine. Oh, look at that. My sines canceled right out. I get the natural log of 1 over cosine theta, which is equal to the natural log of secant theta, the absolute value of secant. We can't take a natural log of a negative number, so we need those absolute value bars around it. So there you have it. We have written that as one particular logarithm. Like I said, I will put something up on my Moodle page that has both a link to this recording if you would like to watch it again, but then also a link with all the properties of logarithms. You have a couple questions on your homework that will use that. So go ahead and get started with the 5.1 homework, and when I get back next week, we will go over any questions you have over 5.1.